Alrighty, welcome back, folks. Let's go ahead and take a look at numbers 16, 17, 18, 19, so on and so forth. It asks 16. The smallest integer n such that 100 over 99 to the nth power is greater than 8 trillion. Well, a couple things to keep track of. Million would be 10 to the 6, billion would be 10 to the 9, and a trillion is 10 to the 12. So 8 trillion is 8 times 10 to the 12. So they want us to figure out what exponent or the number that we can raise 100 over 99 to, and that's going to give us a value greater than 8 trillion. An easy way to do that is throw it into your numerical solver and solve 100 over 99 raised to the n. Now the important thing here is I didn't write it, but make sure that your fraction is in parentheses, because otherwise the calculator will just do 100 raised to the nth power over 99, which is not what we want. Okay. Another important thing to learn, in my opinion, would be you could probably do this a little bit faster if you know about logarithms and you're fluent in it. Taking the logarithm of a number or a base raised to some exponent, that's going to be equal to the base times logarithm of that number. So in this case, n would be the exponent here, and when we apply that trick, we get n times log of 100 over 99. It's going to be greater than, well, now remember, we've got to do it to the other side, log of 8 trillion. So in the calculator, 8 times 10 to the 12, push the log button, 100, enter 99, log, divide, get your n number, and then round up if it's a decimal portion, and there's your answer. Let's look at 17. 17 is really annoying because it's a tedious problem, and it can look really difficult if you don't know the formulas that apply. Now there's a couple ways to relate these numbers, but the quickest way is, if you've taken physics, is if I have a wheel rolling at some velocity v, it's moving along the ground at some velocity v. Well, it's going to be rotating at some angular rate represented by the symbol w, or omega, and the radius. Turns out if I take that radius and I multiply by the angular velocity, that's the linear velocity of the wheel. So if we divide the velocity by the radius, we're going to get how fast it spins. The annoying thing is doing all the unit conversions. So once we have our answer, we'll need, or before we get our answer, in my opinion, we need to convert the velocity, 2 inches per minute. It's originally in miles per hour, right? So here's that conversion. So that when we divide by the radius, we get that guy to cancel the units. Now we could convert radii to miles, but the question is still going to want the answer in minutes, so I figured might as well just convert one set of units, and that's going to be the miles per hour. So once we do that, our answer is going to be in per minute. Now the tricky thing about this formula is that you need to understand that this angular velocity, when the units cancel for length, that's going to give us the units of radians per second. And the question wants the answer in revolutions per minute. The last unit conversion we need to do is to convert this radians per minute into revolutions per minute. Now, on a separate video, we'll talk about why this is, but turns out it takes 2 pi radians to complete 1 revolution around a circle, or 360 degrees. So we divide by 2 pi. Okay. Number 18. The Voyager space probe is moving away from the Earth at 10.6 miles per second, and was launched in 1977, so on and so forth. It gives the distance that it is now from Earth and the speed of light. And they ask, how long does it take a radio signal from Voyager 1 to reach Earth? Well, here we're going to take that distance, 24.56 billion kilometers, and we're going to have to convert that to miles. And that's going to be a factor of 1.609. Once we do that, we divide by the speed of light, because a radio signal is traveling at the speed of light. If you're wondering if you should add or subtract the speed of the satellite relative to the speed of light, no, you don't have to. Now, if this were sound, yes, the Doppler effect would kick in, but that's not a question they ever ask here in the UAL calculator portion. So you just take the speed of light, and the speed of light is always the speed of light, regardless of relative motion. So the important thing here is significant digits. Because we're dividing, we're going to use the least amount of significant digits, which is 4 units. All right, 19. A popular way to solve this question is to write the area of a triangle in terms of the hypotenuse and using sines and cosines. And I explained that in practice. But I'm going to show us another way. That might be a little bit more direct, but takes a little bit more setup. Because this question has us solving for this side, not the hypotenuse. So one way we can relate is these two sides is through tangent, and the reason we want to do that is because the area of this triangle is going to be the base, which is the side in question, times the height here. Using tangent is equal to opposite over adjacent. Tangent of that angle, 0.57 radians, is going to be the opposite side over the unknown side, x. So we can rewrite the height of this triangle, aka the opposite side, as x times tangent of 0.57. Putting that into the area formula, the area here is 2550. That's going to equal the side base, and then times the height, which is x tangent of 0.57, divided by 2. Multiply by 2, divide by tangent of 0.57 on the 2550, and then square root, and there's our answer. Number 20 is another question involving a right triangle and area. In this case, they give us the area, they give us the base, they want us to find the hypotenuse. We could try doing it in a similar way as this question, where it's the base and then the height, and then we do more trick stuff, but we don't have an angle here. In this case, the fastest way is just actually directly base times height divided by 2 equals the area multiplied by 2 divided by 0.368. That's going to give you the height. Square that number, 0.368, square that number, add them, square root, and there's our hypotenuse. Alrighty, that's it for these. Thank you.